Hello, thank you for the presentation. I work in the National Meteorological Service of Argentina, and also I am a PhD student at the University of Buenos Aires, and I'm going to present the experiments we did about assimilation of lightning observations. The first question is why assimilate lightning observations? The main reason is because it's an observation of at convective scale. Here in this image, I show the region where the National Meteorological Service of Argentina performed an analysis, and the only observation at convective scale is radar observation, and is located in this is only in these circles that I show in the image, and as you can see, it's a small part of the domain. So with lightning observation, we could assimilate convective scale observation in a larger region. And also, radar observation present different limitations like beam extinction or wet radome effect that lightning observation could complement in those cases. The observations we trying to assimilate, or we want to assimilate, are from the geostationary lightning mapper, or GLM, on board of GOES satellites. They have a 10-kilometer spatial resolution and 20 seconds temporal resolution, and the variable we will assimilate is the flash extent density, or FED, that represent a count of lightnings and also give an idea of the extension. The first issue we have is that we need to have a lightning forecast to compare with the observations. So the first attempt for an observation operator was a relationship between observations and the forecasted variables, in my case from the WRF model. We perform an analysis in this paper where we shown that vertical integrated ice content is well correlated with lightning observations, but this approach have the problem that we need a regional adjustment if we use it in another region, and also is model dependent. So if in the future we apply some changes in the model, we need to perform an adjustment. The other option is solving explicitly the lightning process in the clouds. For example, the WRF model have the WRF-elec module, but this increase the computational cost, and if you want to use it in an operational environment, this will be a limitation. The approach we take is, as reflectivity and lightning are related to the hydrometeors, we let the machine learning algorithm to learn this relationship. So we train a convolutional neural network, especially a UNet-like architecture, to learn this relationship only from observations, and then take the WRF or any model reflectivity forecast as an input for the convolutional neural network, and get the forecasted lightning. This observation operator, we are now testing it in the regional analysis of the National Meteorological Service during all 2025 year. So to reinforce the idea, we take the analysis reflectivity as an input for the convolutional neural network, and to get the lightning analysis. I didn't mention, but we use the LTKF methodology, the local ensemble transform Kalman filter methodology, to perform the regional analysis. So in this picture, I show you two cases where this is the ensemble, the mean of the ensemble analysis lightning for two cases, and this is the observation. These both regions are well covered by radar observations, so the location of the lightnings are well located with respect to the observation. The intensity not so much, but as I mentioned, this is the ensemble mean, and if we look at member by member, we can see the magnitude of the lightnings are similar to the one observed. And I don't show the lightning cycle, but the daily and annual cycle of lightning are well represented by the analysis and in conjunction with the forward operator. Moving forward to the data assimilation experiments, we try to use a similar configuration from the one used in the operationally in the National Meteorological Service. We use the LTKF methodology with a 40-member ensemble. As these are the first experiments, we didn't use real observations, so we ran a nature run forecast initialized with initial conditions and boundary conditions from ERA 5 and 2 kilometer resolution, and with the observation operator that is previously shown, we generate the synthetic observations to assimilate in a no data assimilation forecast with initial conditions and boundary conditions from GEFS and a resolution of 4 kilometers. The case we use is the 19 March 2024, which was a really challenging one because, as you can see, the NODA forecast doesn't show enough the convection that are present in the nature run and also in the real observations. This both simulation start at 12 UTC. We let 6 hours of spin up, and between 18 and 21 UTC, we perform 10 minute cycles assimilation. The first experiment we did was assimilate only non-zero lightning observations. They are we locate them at 400 hectopascal because at that height there's a peak in the frequency of lightning. We apply a 25 kilometers horizontal localization, and we set a vertical localization, but this is large enough to have impact in all the atmosphere, so there's no an effective vertical localization. In this image, I show the nature run, the ensemble mean NODA forecast, and the lightning data simulation experiment. These both are the ensemble mean, and they are for the 21 UTC at the end of the assimilation cycle. We can see a clear improvement from the NODA experiment. I didn't mention this is the column maximum reflectivity in the forecast. We can see a clear improvement with respect to the NODA experiment, but there's no evidence of this cell in the north of the domain, because there is a limitation in the LTKF methodology that if no members present lightning, you cannot assimilate this the observation, because the model, the methodology doesn't know how to apply the increments in the forecast. And I will show in the next slide how we try to sorry how to tackle this limitation. In this figure, I show you the probabilistic fraction skill score for different lightning thresholds. We can see that at half an hour after the assimilation start, a jump in the skill of the fork in the analysis, showing that related to the development of this cell, and a steady decrease in the along with the cycles. The next experiment was the inclusion of zero lightning observation in order to suppress the spurious convection. It's hard to see in the ensemble mean, but as in the previous slide, if you look at this region, we can see a diminish in the reflectivity, showing the suppression of the spurious convection. And if member you can see more clearly how the spurious convection is suppressed. But the downside is that there is a reduction in the reflectivity, in the low value reflectivity around the convective core. In the previous slide, in the previous experiment, you can see a much clearer low values around the storm. In the probabilistic fraction skill score diagram, we cannot see the much difference, probably because of compensation between the suppression of the convection and the reduction in the low reflectivity values. As I mentioned earlier, to tackle the limitation in the LETKF in the development of the North cell, we assimilate relative humidity pseudo observation if the analysis doesn't have enough members to represent with lightning. This observation is assimilated at minus 10 degrees isotherm, because at that height is where the lightning process occurs. In this case, we see the development of the North cell with the help of the injection of humidity, and also we see a huge increase in the fraction skill score. And something that's interesting to see is that there's higher values of fraction skill score for higher thresholds of lightning, showing that there's more impact in the higher thresholds of lightning. Something interesting is that I don't show is that in the first assimilation cycles, there's a lot of relative humidity of the observation assimilated, and with the development of the cells, this quantity reduced a lot, and there's a peak in the lightning observation assimilated. To sum up, we see that the observations, we see that the machine learning algorithm proposed as a forward operator is well suited for data assimilation. We see a clear improvement in the analysis using the lightning data assimilation, and the sub-observation of relative humidity can help with the convective initiation in the cases where we have the limitation of the LETKF. As a future work, we plan to take did experiments with radar observation also in the cycle. Look at the impact on the forecast. For example, the north cell that was hard to develop in the analysis probably I assume, will decay faster in the forecast. And of course, did perform a real case experiments. And that's all. Thank you.
Thank you, Federico. Please feel free to put your questions in our YoPod. In the meantime, I would start with two of my questions. And the first one, I was curious, great talk first. Thank you for, showing about this novel observation types that can constrain convection. I was wondering if when you have both radar observations and lightning data, in those cases, what are the impacts on the hydrometeor fields? Do you feel like radar observations are sufficient and you can exclude the lightning data if we have both of these together? Or do you see benefits from assimilating both radar and lightning data?
I already didn't perform the assimilation with both observations, but in many papers shows that the analysis is better with both observations than one of one each other, one separated.
So they seem to complement each other if they're both together.
Yes.
The reason I was asking the question is because you made this assumption about the lightning being a function of the reflectivity. So I thought maybe if you have both of these observations, they will be correlated and there will be some redundant information present. So it probably depends also on the observation operator itself. And
yes.
I see a question from Javier. I'll read it out now. How are the error statistics of the observations modeled and handled in your experiments?
Can you repeat the question, please?
Yeah, how are the error statistics of the observations modeled? So what are the observation errors of your lightning data? How do you model them? What are the magnitudes of the error variances in your LTKF?
Yes, I put this information here. We take two flashes per minute for lightning, positive lightning, one flash per minute for the zero lightnings, and we didn't test this a lot. This is more like from previous papers that we read. I hope I answer the question.
I think so. Yeah, this shows the actual values here. Thank you. And then there is a question also coming from Minghua. She's asking, when you assimilate the lightning data, for how long can this impact propagate to your fraction skew scores? How long do you see the impact being present in the future lead times?
No, I already did the analysis. I didn't perform already the forecast from this analysis, so I cannot answer the question now.
Next steps.
Yes.
I think, but something maybe that you have done, I had a question on my own for the lightning assimilation. Is it fair to say that the largest impacts on the analysis fields from this new data is for the storms that have the most abundant lightning activity? Did you see that kind of relationship where you have storms with lots of lightning? That's where you see the largest increments in the analysis.
A great question. We need to probably the higher values of flashes may be problematic because we need to represent this in the forecast, and are the interesting cases, but probably the most difficult to assimilate.
Thank you, Federico. I believe these are all the questions here. Thanks